Okay, so we're going to switch up the agenda just a little bit. Our next talk is actually going to be David Bennett on the Roman Galactic Exoplanet Survey. Cool exoplanets dominate. Dave's going to do this online.
All right, so I'm going to focus most of my talk on development since the selection of W first and then Roman. But this is a slide showing what we proposed to the decadal survey was the microlensing planet finder, which is a much smaller telescope, but focused on doing a lot more microlensing. And so this is a plot from the submission, and then here's a more recent plot showing what Roman can do, and it has a lot of detections from Kepler, which weren't really available back in 29 or 2010. All right, so here's an outline. So I'm not going to say much about the selection, and then I'm going to focus on post-Astro 2010 developments. Um, so these are some of these are results from ground-based microlensing surveys that are going to focus some of our efforts now that when we start getting Roman data. All right, and so the most interesting thing at the end here is just rogue planet discoveries, which seems to imply that apparently rogue planets are more common than any other type of than all the rest of known types of exoplanets combined. All right, so this is just a diagram to show this Einstein radius is a sort of characteristic scale for detecting planets with microlensing. And so you get a ring image when you have a perfect line between a single source and a single lens just by symmetry. But the highly magnified images tend to be close to the Einstein radius, and this is where we're most sensitive. And basically, roughly, order of magnitude, this is equal to the geometric mean of the Schwarzschild radius of the lens and the distance to the lens, and that's a few AU. And this is why microlensing is sensitive to planets at orbital distances of separations of a few AU. And so it contrasts with the transit method, and so it's a reason why microlensing was selected to sort of complete the exoplanet survey that was started with Kepler. All right, so a decade ago, we had the first measurement of the mass ratio function. This is um, two versions of the same figure, and we're going to compare this um, to some population synthesis calculations. And so here we see that we're predicting a lot more planets than either of these simulations, either simulations by the Iden-Lin model and by the Byrne group model, led by Mordesini. Um, and so with migration, then there's a very few planets predicted at in the range it can be seen by microlensing, particularly high mass planets. If they turn off migration, then they fit a bit better, but there's still this gap at at a mass ratio of a bit less than Saturn's mass ratio of 2.5 times 10 to the minus 4. Um, and so this is like a factor of 10 discrepancy, and this was thought to be due uh, to one runaway gas accretion. The idea was um, that the large mass for gas giants was caused by rapid accretion at the end of the planet formation phase, and so you're unlikely to form planets in the intermediate mass range between the mass of planet cores, maybe like Uranus and Neptune, to gas giants like Jupiter and Saturn. Um, and so we didn't we didn't confirm this prediction. and and we think that this might have to do with that the protoplanetary disks have less viscosity than is sometimes assumed in these calculations, and so that makes it harder for the gas to lose its angular momentum to fall in onto the growing planets. And this analysis was confirmed with um, the Corial and Harp's radio velocity sample that also shows no evidence for this gap uh, in the sort of sub-Saturn mass ratio. More recently, there was a paper by the KMTNet group that showed a bit of an evidence at a slightly higher mass ratio. Um, Over here, there's sort of at the Saturn to Jupiter mass ratio, they showed evidence for a dip, um, but not nearly a factor of 10 decrease. But when we combine this analysis from KMTNet with the 29 planets in the MOAA sample published, then this dip pretty much disappears. And in fact, more recent KMTNet data shows there's a lot more, a larger fraction of planets in this region, and so that confirms that this dip may not be real, and certainly is not as extreme as it originally was predicted for this sub-Saturn mass gap. Okay, so Roman is also a big advantage of it is that we can get masses, host masses for a lot of the planets found by microlensing. And this is something that we don't necessarily get directly from the microlensing data because we can find planets that are orbiting stars that we don't detect. And so, you know, one of the detections in this Suzuki sample actually was confirmed to be a white dwarf host, which we could only detect with JWST after we were able to show them the microlensing data indicated that the only option was for the host to be a white dwarf. And so here's a sample of HST data of one of these events, and the lens and source stars are separated by a small amount, and if you fit a single star um, profile to them, you see this sort of dipole project that goes away if you fit a two-star profile. And this allows you to determine a number of different mass distance relations to determine what the mass is. So there's mass distance relations that come from the brightness of the lens in two different pass bands, assuming that's a main sequence star. There's a microlensing parallax effect, which is due to the orbital motion. In this case, it's due to the orbital motion of the observatory, and it's the orbital motion of the Earth in this case. With Roman, it would be orbital motion of Roman. And then the angular Einstein radius, which comes from either finite source effects or by measuring the rate in which a lens and source are separating. And so these give different mass distance relations, and you know, so they all converge on the same solution, and so that gives us confidence that we're really measuring the mass. And uh, and so Roman imaging will review host and planet masses for most of the planetary microlensing events. And here's some results of that a paper we're working on now that shows the mass measurements results of using these 29 planets in this Suzuki sample that I showed before. There's 21 planets in 28 events. 19 of them have mass measurements. Those are shown here. 6 have limits on the mass, and then 4 have giant source stars, which don't allow the lens to be detected. And so here you can see that the blue bands here indicate the mass measurements with the 1 sigma uncertainty. And the cyan was estimated host mass without any mass measurement. And so you can see that a lot of these have mass measurements that are near or even beyond the higher mass end of the relation. Some of these are due to systematic errors in the photometry, ground-based photometry, that weren't discovered until the high angular resolution data was available. Both of these are like that. There's a couple of events that have degenerate solutions. This one does, and this one does too, but the 1 sigma error bars overlap. But anyway, we can use this analysis then to determine what the host mass dependence is given a fixed mass ratio. And we find that it scales as the first power of the host mass. This is also something that seems to fit with radial velocity data, at least with the California Legacy Survey. Um, and yeah, and so this actually implies that it will be a little bit easier for Roman to measure the masses of these host stars because they're more massive, and the more massive hosts will be easier to measure.
Dave, we have 2 minutes.
Okay, so so the final thing is a discovery of free-floating planets, and in particular, so here's two examples, one from Mo and one from Ogle, that have likely masses less than Earth mass. And the MOA analysis included detection efficiency calculations to work out how common these were, and in fact, it found that these free-floating planets are about 6 times more common than other types of planets that are found by other methods, uh, and uh, and so it predicts that Roman will have maybe about 1,000 of these, including something like 600 between the mass of Mars and Earth, and so it's very much um, tilted toward low mass free floating planets. All right. And so one thing we really like to focus on is trying to get mass measurements of these, and this can be done with observations from telescopes separated by the distance between Earth and L2 or the distance between two L2 orbits. And so here's simulations of, so here's one of Roman and Subaru. Here's what the mass distance relations look like, so they converge on a mass. And here's another simulation of a more massive planet with Roman and Euclid. And this has been demonstrated now by a detection of a free-floating planet that had multiple observations from Gaia that allowed to measure this microlensing parallax effect between the Earth and L2. And so we'd really like to get simultaneous surveys of the galactic bulge time domain survey by other telescopes, either on the ground or on or with Euclid. And this will allow us to use the same technique that we use to measure the masses of the bound planets to determine whether these candidate free-floating planets are really actually free-floating, or they have a host star at a wide orbital separation that prevents any microlensing signal from the host star. Okay, that's the end of my talk. So I'm happy to entertain any questions.
Okay. Who's running microphones? Okay. We have one question for you, Dave.
Thank you for the great talk. I just had a question. You were talking about free-floating planets, and you mentioned that we could potentially resolve this if we had two space telescopes in halo orbits. Do they need to necessarily be like 180, well, on opposite ends of the orbit, or could there be other phases of the orbits that still allow for this type of observation?
Well, I mean, they can't be very close to each other, but there's a little bit of sensitivity on the mass dependence that you could measure most easily. If you see here, the Earth mass dependence here is it has these two curves sort of separated by a fair amount, whereas these two are not separated by so much. This is this planet is 100 times more massive, and this is Roman and Euclid, which have a smaller separation. Um, uh, but the separation can be 20 or 30% of the Earth to L2 separation. So it is not there's not a huge difference, but it would be unfortunate if Roman ends up in an L2 orbit that is very close to the Euclid orbit. Although that might give us sensitivity to much lower mass free floating planets, but there is also then a potential problem if the planet mass is too low, then then the finite source effects may watch out. I mean, then the Einstein radius of the planet may be much smaller than the angular size of the star, and that makes it harder to find the planet.
Thank you. Okay, so let's give David a hand.